Hi, so this is going to be a video introducing you to the main idea in Chapter 22, and that is Gauss's law. So this is a different way that we can determine the electric field for a lot of configurations. And it's a really powerful tool. So you've seen how you can calculate the electric field by integrating some differential electric field for distributions of charge. Well, this is a often much more elegant way of computing the same thing. So before we can talk about what Gauss's law is, though, we have to introduce one idea, and that is electric flux. So flux. Um, Symbolically, we write it like this. Uh, capital Phi. And it's equal to E dot A, where E is our electric field, A is an area. And the dot product tells us we want these to be aligned in the same direction for maximum flux. And it's a little bit confusing to think of an area as having a direction. But let me show you, kind of draw a cartoon for you. So imagine you have some electric field that's uniform, and the area, think of like uh, a disk. So the area vector is perpendicular to the area. So if this is a disk, the area vector would be of some area A. The area vector would be pointed like that. So in this case, you can see the area vector and the A in the electric field vector are basically pointed in the same direction. And so in this situation, E dot A would be basically EA. In other words, recall that we can also write the dot product as EA cosine theta, where theta is the angle between them. So this would correspond to the angle being very small. Cosine theta is very close to 1. So this becomes essentially EA. And this would be, kind of the maximum flux scenario. To be distinguished from, another situation where, imagine it's kind of the same deal. We have electric field, but now we're going to tilt our disk so that it's pointing down. Now in this situation, EA cosine theta, i.e. that is E dot A, is going to be very small because E is more or less perpendicular to A. So theta is, around 90 degrees. In that situation, this cosine is going to go to 0. This thing will be very small. So the flux, so if this was the maximum flux case, this would be the flux goes to 0 case. So very little flux. And this idea, being able to conceptualize this flux, imagine, field lines passing through some area, is what undergirds the Gauss's law. So we're going to have to wrap our heads around that and be able to add up flux for different kind of geometrical configurations. So Gauss's law is the following. If you add up the electric flux, so in other words, if you integrate it over some closed surface, so this little, here, we'll make an aside here. This is an integral over a closed surface. So think of, like a beach ball or something that's that covers, that goes all the way around. That is going to equal the charge enclosed by that surface over epsilon naught. So this is Gauss's law. This is a really powerful tool. Much of solving problems with this involves coming up with a integration over an area that's kind of a good geometry that makes it easy to solve the problem. So let me show you kind of the first couple examples so we can connect back to what we've already been doing. So imagine we have just a charge, a point charge hanging out. And for a point charge, we could use a spherical surface. So this is going to be the closed surface we're going to make use of. And so recall, for this, the electric field lines are just going to point out from this charge, if this was a positive charge, say. And they're going to be, perpendicular to the, the sphere. And if you think about it, the area vector, since the area vector would be pointing radially as well everywhere on this sphere, it means that E and A are going to be aligned. So in this situation, this is very convenient for us because our E dot dA is going to become just E dA. Now here, let me actually write it in steps. And I'll put Y here as well. So this is our starting point. So a couple important things. So like I mentioned, since E is going to be aligned, it's parallel with the area vector, it means that our dot product goes away. And then, so we can rewrite this as EDA. Now, another thing is, notice if you draw a sphere around this, you know that that electric field, like we talked about this before, it's symmetrical. It's spherically symmetrical. So if you're drawing a sphere, you're at constant r. So that means that the electric field at the surface of that sphere is going to be the same for every point on the sphere. So I'll state it this way. Because it's the same distance, E is constant at the surface. So what that means, if you have an integral and you have a constant in there, we can pull out the electric field. Now we just have a surface integral of the sphere. And this is just a sophisticated way of saying that we need the area of the sphere. So we know what the area of a sphere is. Actually, let me use big R because that's the way I have it in my little cartoon. Hey, and look, now if we divide by our 4 pi r squared, we have our expression for E again. So this is a different way to come up with the electric field around a point charge using a different, different mathematical tool. Now, this example is maybe like not, super surprising, or I think it's clear where this came from, but maybe it's less clear that this is, I've been harping on how this is so useful. Let me show you another situation that we looked at before, and I think you'll see how this can be pretty useful. So that's the line charge. So for this situation, we have a linear distribution of charge, and our Gaussian surface would be a cylinder that's concentric with this line of charge. And let me call the line, the line is going to have some linear charge density, lambda. And, just like with the sphere, we know the electric field is going to be, radially outward. So we can set up our Gauss's law problem here. That the closed integral of the flux is going to equal the charge that's enclosed by our surface over epsilon naught. Now, again, this would have some radius r. And let's also give this a length L. So this way we can state explicitly what the charge enclosed is. It would be lambda times L. Okay. Now, E dot dA, the only part of this that's going to contribute, or I should say a couple things. So just like with the sphere, since E and A are pointed in the same direction, they're, E and A are parallel. Or not A, dA. It means that the dot product is just going to become E dA. And then also, since, if we're looking at this at the top, it looks very similar to the sphere. Since this R is the same distance from the wire, it means that E is going to be constant. At R. So we can simplify this. E dot dA becomes E times an integral over the area of our cylinder. Now, what's the integral? What's the area of a cylinder? Well, we would have 2 pi r times the length of that cylinder. Now, notice I omitted the ends of the cylinder, and this is because, remember when we were talking about this problem, this was really long. And also, the ends would be perpendicular to the flux that we're describing. So in other words, we're talking about like in the middle of the of our long, infinite line of charge. Um, but notice, check this out. So the L would cancel. It appears on both sides. And then we can solve this for E. What do you have? You have lambda over 2 pi epsilon naught r. So this we've recovered, not cylinder, the electric field for a line of charge. Notice we did this in a few lines of math. When we did this by integrating dE, it was much, much more complicated. So, this is much simpler than this approach. So, I hope this gives you a little bit of, confidence, or shows you that some of the stuff that we're going to be doing next is going to be, a lot more tackleable than some of the more complicated integrals and stuff that we encountered in the last chapter. So, and I'll follow up this with giving you some examples to show you how to solve problems using Gauss's law.